All right, so let's now talk about the lenses used in electron microscopes, particularly SEM, since that's what we're talking about now. So we have an electron beam, and as I said in the lead up to this, that means that we can't use simple glass lenses like is used in light microscopes because glass lenses won't focus electrons like it does light. So to serve that same purpose of focusing, um, we need to use electromagnetic lenses or EM lenses. And so that's what we use here. And so this is kind of a schematic showing the cross section of what one of these lenses actually looks like. So, but first, before we get to that, we've produced this electron beam with the electron gun, and we're accelerating at the specimen. And so the purpose of these lenses, as it was with light microscopy, is to focus that beam now into a small diameter so that we can form the image. And that's what these electromagnetic lenses do. And they focus these electrons by deflecting them. That's how we have to have those. One thing about the electron beam itself, so this schematic here kind of shows the electron beam coming down from the electron gun, which is usually at the top, through the lens. And one thing you'll notice here is that this electron beam doesn't move in a linear fashion. It actually moves in a spiral down the axis. So it's not just linear, it actually spirals through the lens. And this is an important part of how the electrons are focused. So again, they're not deflected by glass lenses. We need these electromagnets to create a magnetic field, because that magnetic field can deflect any off-axis electrons. And so that's what's done here. So effectively, this lens, all it really is this huge electromagnet. And so we have a conductive wire that's wrapped around. And so you kind of see that the green cross section of those wires. And when we pass current through it, we get a magnetic field. And so you can kind of see these magnetic field lines in red that are being emitted from the electromagnet. And so basically you have magnetic fields that are the components here, B, so that's what we use to describe the magnetic field. And basically, since it has this sort of elliptical nature to it, or curved nature to it, there's a component of that magnetic field that is radial, as it's called, R. So it's basically towards the radius of the lens. And then there's one longitudinal component, which is down the axis. So there's basically two components of the magnetic field. And that's what's being shown. And so these two components basically act on the electron, and they really only act on those non-axial electrons. So if it's following the path down, then there's no force on the electron. It's only these off-axis ones, like the ones that are over here, that have force. And so basically that force on the electron causes them to spiral closer to that optical axis. And so that magnetic field that's produced creates a force, and they become closer and closer to the optical axis. So that gives us a smaller beam, and that causes the crossover, right? The beam diameter to decrease, and it causes them to converge in the same way. So that's the purpose of these so we can manipulate the magnetic field in these lenses to create the beam that we need. And so typically in an SEM, and also in TM as well, but typically here we would have two of these condenser lenses that would be responsible for decreasing this crossover diameter of the beam. So basically doing what it's showing here, we'd have two of those for that. And so that kind of takes us to the fact that we have this beam and we're creating a much narrower diameter of that beam. And so next we want to kind of look at the probe size, right, the beam size, and current, and see how all of these things are affected. All right, so we've taken a look at the gun and the lens, and so let's look at now the beam as it comes out of that configuration. And so we see that the electron crossover point, or the probe diameter, this ends up being what controls the resolution of the SEM. And so therefore, this is a very important concept. All right, so past the lenses, we also have a final aperture. And so if you can kind of envision the electrons converging past this aperture, so they're basically converging, and they're going to converge onto the specimen surface. And so this is the diameter of the probe, and that's listed as little small d and then subscript p. So that's the probe diameter, or the cross, and that is the diameter of the crossover point. So it converges from the final aperture to this, and so therefore the angle, just like it was in light microscopy, coming from the final aperture to the crossover point is alpha. So that's the aperture angle, alpha, in that case. And we also have, along with that, the distance from the final aperture to the specimen is known as the working distance, and sometimes we represent that as just WD. So we have that as well. One other thing that you see here on this drawing is the actual electrons in this beam that are crossing over have, since there is a flow of electrons from the gun down to the specimen, we can represent that flow as current. And so that tells us about sort of the intensity and so forth. And so the current of the electrons is known as little I P for probe. Okay, so let me switch over to the paper, and I'll give you an expression that gives us the probe diameter as a function of some of these parameters. All right, so we can approximate the probe size by a number of factors. And so again, we refer to the probe diameter as d sub p. And so this is equal to 4 over the current, and then beta pi squared alpha f squared, and all of this is to the 1/2. So just to kind of go over some of this, again, this is the probe diameter. I sub p is the beam current, or the probe, however you want to refer to it, probe or beam current. Beta is known as the beam brightness, and so this is going to be controlled by the electron source. So if we have a tungsten source, or we have a lab 6, or if we have a field emission, that's where you're going to get this beta term. And then alpha f, as we said before, this is the convergence angle of the probe. This is basically the same thing that you see in light microscopy, which is the aperture angle in that drawing. So this is from the final aperture to the sample's surface. So the distance for the working, the working distance that we see. All right. So these are all the terms, and this is how the probe diameter is controlled by current. So you can see here that if we increase the probe current, we increase the diameter. If we and then it would have inverse relationships, obviously, with brightness or the aperture angle or the convergence angle that we were talking about here. So to give you a reference point for B, I'm going to go back to the slides and give you a table here for beam brightness values for the different materials. All right, so this is going back a couple slides. This is table 3.3 in your textbook, and it compares some of the electron guns that we talked about before. And so this brightness term here that we see, that gives you an idea of the beta term in our probe diameter equation. And so these are all approximate brightnesses. You will note that it is as specific accelerating voltage, and so those would obviously change if the accelerating voltage were different. And so these are just approximations of that beam brightness. All right, so we saw from the previous table on the slides that the field emission gun has the highest brightness, followed by lab 6 and the tungsten filament. But also the beam brightness, beta, is proportional to the charge of an electron multiplied by the accelerating voltage. So we can increase the brightness by increasing the beam voltage. So that's one way we have to adjust this. So just overall, if we sort of step back and go to the probe size equation, the probe diameter, some of the big takeaways that we see here is that, again, the way we define resolution, we say that resolution increases, but really what that means is that the probe size decreases. So to achieve that, we can increase the brightness, we can increase the convergence angle in this expression, but we can also, if we increase the angle here, this actually leads to some other problems. And so really what we have to do is kind of optimize this expression, because we find that spherical aberration is a problem when this increases. And so we can't just completely increase this angle. We have to consider sort of an optimization. And therefore, if we kind of consider some of those factors in, we can get to a minimum diameter, and this is equal to K CS to the 1/4, and then IP over beta plus this lambda term, and then all of that is to the 3/8. So obviously it's kind of a clunky equation there, but some of the things to note about this one: K is a constant, and it's close to 1. CS is the spherical aberration. So we talked about this type of aberration when we looked at light microscopy. So we still have these effects in electron microscopy. This is actually a big type that we try to correct for. And then lambda here is the wavelength of the electrons. So often, we think of electrons as particles, but we can also think of them as waves. That way it's more comparison to the other types of microscopy that we look at. So if we, considering this equation, I'm going to hop back over to the slides and show you a little bit more that gives you an idea of this minimum diameter. All right, so now we know that probe size not only depends on brightness and the current, but also spherical aberration and the electron wavelength, which are two factors we added in when we consider the convergence angle. If we increase that, we actually have to, we can actually bring up more problems, and so that's what we have there. And so this figure here kind of illustrates what we can kind of expect with all these parameters. And so we have current plotted, and then the diameter. So that's obviously what we're trying to achieve, the smallest diameter possible. And so we can see that if we decrease the current, we decrease the diameter. So that was what we saw from the first equation. So that's a big trend that we see. And then we can also see that if we go from tungsten to lab 6 to the field emission, we decrease the diameter as well, therefore increasing resolution. And so that was inherent to the beam brightness in that as well. And so that can also achieve that as well. But again, also we can decrease the wavelength. So that came out of the second equation. So if we want to increase the resolution, we can decrease the wavelength of the electrons, and obviously the decrease spherical aberration, which was that C sub S term as well. So we definitely want to do that. But we also want to increase brightness. So overall, the resolution follows that same trend that brightness did, where field emission followed by lab 6 followed by tungsten is the order of maximum resolution. So it increases in that same order. All right. So the last part that that we didn't mention as much, and this goes to the wavelength. So the wavelength isn't something if you sit down at an SEM or a TEM that you can think of as kind of turning a knob. You're not directly changing the wavelength, but you can adjust the wavelength by adjusting the acceleration voltage. So this shows you that illustration. So by increasing the acceleration voltage, we decrease the electron wavelength. So we want to basically, if we want to get smaller probe sizes, we decrease the wavelength or increase the acceleration voltage. So wavelength isn't necessarily the knob we turn, but acceleration voltage is something that we have direct control